Now, so yesterday we looked at Fermat's little theorem, how to use it to get remainders. So basically what we were doing was just getting remainders whenever we had something like, let me just write something, remind you what we were doing. So, in cases where we had something like, let's say 9 raised to a number here, mod prime number. This is what we were doing yesterday using Fermat's little theorem, and we said by Fermat's little theorem, if this p does not divide this number, then we would say that this number 9 raised to p minus 1 is congruent to 1 mod p. So that's what we did yesterday. But now today we want to use Fermat's little theorem to get inverses. So remember, inverses are very important in blockchain and cryptography, because whenever there is encryption, to decrypt, you have to use the inverse. So that is why we have to know how to get inverses for the purposes of decrypting and so on. Now, so what does Fermat's theorem say about inverses? Fermat's theorem says that if you are given a raised a mod p, where p is prime, and this p does not divide this a, just as we did yesterday, if p does not divide a, and if p is prime, then we can get the inverse of a as a raised to p minus 2 mod p. So that is what it says, that the inverse of a can be obtained. And how do we get it? We take a and raise it to p minus 2, then do mod p, reduced by mod p. That is how we do get inverses using Fermat's little theorem. And you know, this is a very fast way of finding inverses compared to other methods. So we have other methods. We have the Euclid's extended Euclid's algorithm, which does the same thing. But again, Fermat's little theorem is only restricted to when p is prime. When p is prime, but Fermat, the extended Euclid's algorithm would do for all numbers. It doesn't need to be prime at this point. This one doesn't need to be prime for you to use the extended Euclid's algorithm. But now Fermat does your work easier, faster. The only condition is that this must be prime and it should not divide a. That's the only condition. But it's a faster method than the Euclid's algorithm. Now, so, and of course, you know, when you are in blockchain and cryptography, you're using prime numbers. And so Fermat's theorem, it becomes very important, because what we will be using will be prime numbers. And so you realize then it's important to learn it, because it's faster. And again, we'll be dealing with the prime numbers most of the time in encrypting and decrypting. Let's find the inverse of 7 mod 23. Of course, 23 is a prime number, and the 23 cannot divide 7, and therefore we can use Fermat's little theorem. Now, so what does it say? It says that the inverse of 7 mod 23 is just the same as 7 raised to 23 minus 2 mod 23. And when I subtract 23 minus 2, what I get is 21 mod 20. So this is the inverse, mod 23. This is the inverse. The only thing you need to do now is to use the fast powering algorithm and find out what is this remainder on a division by 23. What is this 7 raised to 21 on division by 23? That's the only thing that remains. But you, of course, we already know what the inverse is. The inverse is 7 raised to 21, but we reduce it, make it smaller. Now, first pairing algorithm, we are doing, want to find 7 raised to 21. So what is 7 raised to 1? 7 raised to 1 is 7. And then 7 raised to 2. Remember, we always square what is above. We square this, the whole line. This is 7 raised to 2, and this will be 49. And we are doing it mod 23. So 49 mod 23, we just asking ourselves, if 23 were to go there, what will be the remainder? I can see it will go there twice because of 46, and therefore the remainder is 3. And that is what I wrote here. Now, we square what is above, we get 7 raised to 4. And then also square 3, you have 9 mod 23. Of course, 9 is less than 23, so you have no problem here. It's less than 23. But whenever it is greater than 23, you have to reduce it. You have to divide by 23 and find the remainder. 7 raised to 8, of course, again, we square this line, the entire line. When you square that, 9 square is 81, which is larger than 23. So you have to divide by 23 and not the remainder. Let me just go to my calculator, as you also do the same. Find your calculator so that we can move fast. Now, so 81 times. So what is the remainder after going there 3 times? The remainder is 12. That's what I wrote here. Then again, square this line to get the next line. 9 raised to 16, the same as 12 square is 144. We are doing it mod 23. Mod 20, that means we are dividing by 23 and noting the remainder. So 144 divided by 23 goes there 6 times. What is the remainder? After going there 6 times, the remainder is 6. And that is what I wrote here. Now, we would have proceeded, but when you proceed, you realize you'll be having 7 raised to 32 because you are squaring this line. But what we require is 7 raised to 21. So 32 is above what we want. That means we stop where we reached. We just stop there. Then now go straight to the result. What we want is 7 raised to 21. How do we achieve this using what we have? This is what we have. How do you achieve 7 raised to 21? You notice that it will be the same as 7 raised to 16. How do you achieve 21? It will have been plus 5, but 5 is not here. It's not one of the powers. So I can see 4. So you can add 4 here, then add 1, which I can also see here. So you're only using what we see. What we have is what we use. So we have 16 plus 4 plus 1, giving us 21 as the power. Now, so this then means that this is same as 7 raised to 16 using the laws of indices. 7 raised to 4 and 7 raised to 1. What is 7 raised to 16? We have it. We have it as 6. What about 7 raised to 4? We have it as 20. What was it? 9. We have it as 9. Then 7 raised to 1, we have it as 7. Now, so you can multiply those numbers and then divide by 23 to find the remainders. Just do that together. So what we have is 6 times 9, then times 7. That is 378. 378. Let's divide by 23. Goes there 16 times. What is the remainder? After going there 16 times, the remainder is 10. That's what I'm getting using my calculator. So this then becomes the inverse. This is the inverse of what we were looking for. We're looking for the inverse of 7 mod 23. So that then means that the inverse of 7 mod 23 is 10. You can verify this. You can verify by, how do you verify? You know how to verify. You can verify by multiplying this 7 times 10 and then do it mod 23 and see whether indeed it gives you 1. Because if it gives you 1, it means then it is true that it's the inverse. Let's see. That would be 70 divided by 23. Those are 3 times. Then what is the remainder? The remainder is 1. So we are correct. So that means you can always verify if you have the correct inverse. In fact, the other way, using the Euclid's algorithm, instead of writing this, we had said using the Euclid's algorithm, this will be the same as 7x is congruent to 1 mod 23. So that means our x here is 10. Our x is 10. Our x is 10. That's what it means. 10 times 7 gives you 1 mod 23. In fact, that's what we got here. That's what we got. Now, again, I just want to show you how to do this so that we are familiar with it. Let's do the next example. I want to find the inverse of 12 mod 19. So again, if this is prime, and if it cannot divide 12, then our method, Fermat's little theorem, comes in. But if it's not if this is not prime, then you can never think of Fermat's. You have to think of either the extended Euclid's algorithm or the Euler theorem. Of course, we have other methods, but I taught you those two. I taught you the extended Euclid's algorithm and the Euler theorem. So if this number is not prime, then those two, you think of those two. But if this number is prime, then let's think of the Fermat's little theorem. So what does it say? That the inverse of 12 mod 19 is the same as 12 raised to 19 minus 2. 19 minus 2 mod 19, which is, of course, 12 raised to 17 mod 19. So once you reach here, you then now use the first powering algorithm. That is the successive squaring method. So first thing we square is 12 raised to 1, which is 12. Then a 12 square, which is 144. Remember, we are doing mod 19. What is that? It means that our divisor is 19. So we are dividing by 19 and noting the remainder at every point. Let's just do that. 144 divided by 19 goes there 7 times. You're using your calculator also. So if it goes there 7 times, what is the remainder? I'm getting 11. Now square this line to get the next line. Square this line. So when you square it, you have 12 raised to 4 is congruent to the square of 11 is 121. And we are doing it mod 19. So what do we get? Mod 19 means divide by 19 and not the remainder. So that is just, suppose there's somebody who is new and doesn't know what we are doing. That's what we are doing. Mod 19, that's what it means. That divide by 19 6 times, because there are 6 times, and then not the remainder as 7. Now square that line again. What you get is 12 raised to 8. and then square 7, which is 49. You can see that 49 is bigger than 19. So that means you have to divide by 19 again and not the remainder. So dividing by 19 there, goes there 2 times, goes there 2 times, and the remainder is 11. Let us again square, because we want to go up to the power of 17. We want to go up to the power of 17 or close to it, very close to it. So when we square this one, you get 12 raised to 16. And squaring 11 again, what we get there again is 121. The first time we got 121, the remainder was 7. The remainder was 7. Okay, can we square it again? Let's see. Let's see if that is possible. When you square this, we shall have 12 raised to 32. This is beyond what we want. Is beyond what we want. So that means we cannot take that route. It means we've reached where we wanted to go. It means we are already there. So what we are only supposed to do now is to find out what 12 raised to 17 is in terms of what we have. In terms of what we have. So in terms of what we have, is the same as 12 raised to 16 plus 1. 17 is the same as 16 plus 1, which is the same as 12 raised to 16 times 12 raised to 1. What is 12 raised to 16? We have it as 7. What about 12 raised to 1? We have it as 12. This gives 84. And remember, our divisor is 19. So how many times does it go there? Our calculator comes in handy. So we have 84 divided by 19, goes there 4 times. Goes there 4 times. And the remainder is what? The remainder is 8. The remainder is 8. So in other words, therefore, as a minute. Therefore, the inverse of what was it? 12 raised to the inverse of 12 mod 19 is 8. And as I said, you can verify. You can verify by just multiplying 12 by 8 and get what? Get 96. And what is 96 mod 19? Let's see. 96 divided by 19 to be 5 times. 5 times, and the remainder will be 1. So we have verified that. Any question up to there? Any question up to there? And if there's a question, is good, you just raise your hand so that I can answer a question in real time. Otherwise, when you write the charts, I may not see it. I may see it at the end of the class. So when I answer it, it may not assist at that point. It's good I explain the answer. I explain what I'm doing at the time when I'm still doing it, so that you can relate very well. Now, so the first 2 examples that we've been doing, the number coming before the mod was smaller than the number after the mod. For instance, you can see 12 here is smaller than 19. So the first 2 examples that I've looked at, you can see even for this other example, 7 was smaller than 23. So I now want to change and look at if the number before the mod is larger than the number after. Those are the examples I want to look at therefore. Now, so I want the inverse of 35 mod 29. This number is bigger than 29, so we begin by reducing it. So what I know is that 35 mod 29 is just the same as 35 into, no, 29 into 35, the remainder will be 6. So it's just the same. These two are the same. They're giving us the same remainder. So somebody's saying that find the inverse of 35 mod 29, and another one saying find the inverse of 6 mod 29. The two people are saying the same thing. The two people are telling us the same thing. So instead of even finding the inverse of 35, we can deal with 6, the inverse of 6, because 6 is smaller. It's good always to deal with the smaller numbers. So we can deal with the 6. Let's deal with the 6 now. What is the inverse of 6 mod 29 according to Fermat? It will be 6 raised to 27 mod 29 according to Fermat's little theorem. Let me just write properly there. Mod 29. So it will be the same thing. That's what it says. It says a raised to p minus 1, no, p minus 2. A raised to p minus 2. That is the inverse of a. Therefore, the inverse of 6 will be 6 raised to p minus 2. Our p is this. Minus 2 will be 27. Now employ the first powering algorithm. Employ the first powering algorithm. What is 6 raised to 1? This will just be 6 mod 29. What is 6 raised to 2? That will be 36. We are doing it mod 29. What is the remainder? Is 7. What is 6 raised to 4? Remember, we are squaring just the one just above. The line just above. When you square this line, you have 6 raised to 4, and then you square that, you have 49. And we are doing it mod 29. So 29 will go here once, and the remainder will be 20. Square that line, you have 6 raised to 8. And square this, you have 400. And what is the divisor? The divisor is 29. So when you divide 400 by 29, what is the remainder? Is what we note. Let's just do it using a calculator. So that is 400 divided by 29. Goes there 13 times. So times 13, that is the remainder is 23. Next, 6 raised to 16, just squaring the line just above. Square this line just above. So this gives you a square of 23, which is 529. In fact, the square of 23, I don't need to write 529. That's a very big number. I would have written a smaller number, and I'll show you. Now, 529 mod 23, mod 29. So mod 29 goes there 18 times. Goes there 18 times, and the remainder is 7. I had promised to show you that you don't need to write bigger numbers like 400, like 520. These are very big numbers. What we know is that this will be the same as 23 mod 29. Just subtract 29 from 23. what we have is 6 negative, and then negative 6. So because you're squaring, which then gives you that 6 mod 29, which is 7. So you can do it that way. You can deal with the smaller numbers. Now, we're squaring the line just above. Let's try to square it again. 6 raised to 32, and discover that it's beyond what we want, because what we want is 6 raised to 27. So that means we cannot square again. So it means we have reached the end of squaring. What remains is just now the result. And what is the result? 6 raised to 27, therefore, becomes 6 raised to 16 plus 8 plus 2 plus 1. You're only using what you have. What we have are these ones. So those are the ones we then use. Okay. The law of indices says that when you have this, we can rewrite it as 6 raised to 16 times 6 raised to 8 times 6 raised to 2 times 6 raised to 1. But what is 6 raised to 8? 6 raised to 8 is 23. In fact, you can write 23. Or 6 raised to, oh no, 6 raised to 16 is what I want. Just a minute, let me clear this so that I can see. In fact, this one, if you want, this one, instead of writing 23, since we are doing it mod 29, you can write it as negative 6. So that we are dealing with a smaller number. And even this one is very big, you can write it as negative 9. These bigger numbers you can always reduce. So that 6 raised to 16 is 7. 6 raised to 8 is negative 6. 6 raised to 2 is 7. And 6 raised to 1 is 6. And now your calculator comes in. In fact, you can do without your calculator because we know that this would be negative 42. Negative 42. If I taught you how to do this, because it's negative 42, you're dividing by 29. Ask yourself, if 29 were to go into 42, it is negative 42. 29 is going there. If 29 were to go into 42 without the negative, how many times will it go there? It go there 1 point. So instead of the 1 point, we write negative 2 here. So what is negative 2 multiplied by 29? It will be negative 58. And then subtract. So what we have is negative 42 minus 58, which is 16. 16 is the remainder here. So these two are giving us 16. What about these two? That will be 42 divided by 29 to go there once. But the remainder is 13. So you have 16 times 13. Just erase this. I'm just showing you a different way of doing these things whenever, because I already told you that sometimes the numbers could be bigger than you can handle with your calculator. So you have to pair them, you pair them. Then after pairing, you work with them. So what is 16 times 32? 16 times 13. That is 208. 208 divided by 29. Those are 7 times. 7 times. The remainder is 5. So these two are giving us 5. So that 5, therefore, is the inverse of that 5. Therefore, the inverse of that 5 is 5. As I said, if you want, always you can verify. Take that 5, multiply by 5, and you are doing it mod 29. So that 5 times 5 is 175. 29 goes there 6 times. 29 goes there 6 times, and the remainder is 1. Mod 29. Any question there? Now, if you don't want to pair, but I said pairing is very important because of very huge numbers. And again, I've showed you that whenever you have huge numbers, always reduce them. I called this one a huge number, this 23, I call it a huge number. And you can see how I reduced it to a smaller number so that my calculator can handle. Every time you have a huge number, think of how to reduce it so that your calculator can handle it, can handle those smaller numbers. Because if they're very huge, you reach somewhere and then your calculator says math error, or it gives you something times infinite, something too huge. Always reduce the bigger numbers to smaller numbers if you're using a calculator. But now if you're using a program, the program it will just do this math. It will just do it. Now let's do the inverse of 381 mod 47. So somebody giving me 381 mod 47. Another one give me 5 mod 47. They've given the same thing. Because 47 goes into 381, how many times? And the remainder will be 5. Let's just find out how many times. 381 divided by 47. It's 8 times. It's 8 times. And the remainder is 5. So somebody giving me 381 mod 47. Another one give me 5 mod 47. It's the same thing. The remainder is the same. Because this means the remainder, and this one means the remainder is the same. So that means therefore also that if I'm given 381 inverse mod 47, this is the same as the inverse of 5 mod 47. It'll be the same thing. But now, what does Fermat say? Because today we're just using Fermat's little theorem. What does it say about the inverse of 5 mod 47? It tells us that this inverse is in fact 5 raised to 45. This is what Fermat say. Once you have this, the first powering algorithm is a very fast way, as the name suggests. It's a very fast way of finding this. So we just begin again. What is 5 raised to 1? That'll be 5. 5 raised to 2 will be 25. So you're squaring this line to get the next line. We are doing it mod 47. The number before the mod is small, so just leave it the way it is. Let's square this line to get the next line. 5 raised to 4. This will be 625. 625. What is that? Mod 47. 625 divided by 47. 13 times. 13 times. The remainder is 14. The remainder is 14. Square this line to get the next line. 5 raised to 8. 14 square. 14 square. 196 mod 47. And we are asking ourselves, what is the remainder on division by 47? 47 goes there 4 times. So what is the remainder? It's 8. Square this line to get the next line. 5 raised to 16, 64, mod 47. So the question is 47 into 64. How many times? And the answer is 1. What is the remainder? 17. Can we square another time? Okay, let's square that line to get the next. 32. Squaring 17, what do you get? Just a minute. Squaring 17, what do you get? 289. 289 mod 47. Remember, this is the divisor. 47 there is the divisor. So we ask ourselves, 47 into 289, what will be the remainder? Of course, it goes there 6 times. What is the remainder? The remainder is 7. Can we square next time? Let's see. When we square, it shall have 5 raised to 64. Let's see what we want. What we want is 5 raised to 45. 64 is above what we want. So that means we don't require it. We don't require 5 raised to 64. So it means we've reached the end of squaring. So we only require now to write what we need. What we need is therefore 5 raised to what? 45. And this will be the same as 5 raised to 32. I'm left with 13. I'm left with 13 to add here to get 45. But 13 is not among what I have as the powers here. The powers that I have 16, which is more than 13, so I don't require it. But I may require the 8. So that this gives me 40. I'm left with the 5 to add here. I'm left with the 5. 5 is not among these powers. It's not among these powers. The closest I have is 4. What do I have now here? I needed the 5. I got 4. So I'm left with 1. And I have it among my powers. I have it among my powers here. Let me just confirm that what I have is 45 as the power. 40 plus 5, yes, I'm there. You can still hear me, is that okay? Can you still hear me? Because I've seen something like internet connection is somehow low. That's why I need to confirm. It's okay. Now, so this is the same as 5 raised to 32 times 5 raised to 8 times 5 raised to 4 times 5 raised to 1. 5 raised to 32, what was it? 5 raised to 8, 5 raised to 4, and 5 raised to 1. Let's multiply and divide by our divisor, which is 47. Okay, my calculator is ready. 7 times 8 times 14 times 5 gives me 3,920. And I'm doing this mod 47, but the number is huge. It's bigger than 47. That means I have to divide by 47, which will go there 83 times. 83 times, and what I require, in fact, is just the remainder. It's 19. The remainder is 19. So what does this tell me? This one tells me, therefore, that the inverse that I was looking for, mod 47, is in fact 19. Mod 47 is 19. You can verify by multiplying this 381 times 19 mod 47 and see what you get. So let's just multiply and see. 381 times 19 is in fact 7,239 mod 47. And what is this when you divide by 47? 47 goes there 154 times. 154 times. And what is the remainder is 1. Our inverse is correct. I want to take the last example of how to use Fermat's little theorem to find inverses. And this time, I now try a huge number, huge prime, a huge prime number. Although this is not a huge, it's not huge. You can have a prime number that is huge than this. There are so many. The one that you can write a whole page and you're still writing a one number. Those ones can be regarded as huge. But for use of a calculator, this one appears to be huge because I'm using a calculator. I want to get the inverse of this number. Is it bigger than the prime? Yes, this one is 7,000. The prime is 1,000 or something. No, 17. Eh? It's not huge. Which one is bigger here? Which one was I doing here? But why did I do this? I took this number to be I began by writing the answer. Let me just go to the bottom and see what I did. I wrote the answer. I wrote the answers. I began by writing the answer. In fact, this question, what I had done, I had left it for the student to do, but then later on I came and did it. So I had left it for the student. I decided the student should do it and get 1284 as the answer. I decided the student should do it and ensure that it gets 1284 as the answer. So I began by, so then later on I came and did it. And I forgot to erase my answer. Yeah, so that is why I was wondering what is happening here, because I can see the number is smaller. So let's assume that the 1284 is not here because it's the answer we are looking for. It's the inverse that we're looking for. Let's assume it's not here. So the question is, what is the inverse of this number? And Fermat's little theorem says that the inverse of this number will be given by 7814 raised to p minus 2. P minus 2 be 17447. That would be p minus 2. So at this point, we now want to use the first pairing algorithm. And since, according to me, this number is huge, I decided to, first of all, convert this power to binary so that I can see how many times I'm going to square to be sure that I can do it. So using the binary, changing this number, this power here to binary, and I taught you how to convert bases of numbers earlier. This number convert to binary gives me this. So how many times am I going to square? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 times. I'm going to square 15 times. So now I am ready to do that. I'm ready to do that. I was just confirming the number of times I'm going to square because it could be uncountable and I didn't want that. So let me square the first time. This number raised to 1 is the same number. Square this line to get the next line to be 7814 raised to 2. Let me use my calculator and see what I get. Let me see whether my calculator can do that. Just squaring 7814 times 7814. Hey, I have a huge number here. I have 61,058,000. Let me say 61,058,596. What is our mod? Our divisor. Let me just go back and find what our divisor is and write it somewhere. Our divisor is supposed to be 17,449. So this 61 million divided by this 17,449. It goes there 3499 times. 3499 times. Okay, let me find the remainder therefore. What is the remainder? 3499. The remainder is 4,545. Now square that line to get the next line. When you square this line, you arrive here. What is this squared? Is that 45 times 45 gives me 20,657,025. What is our divisor? Our divisor is 17,449. How many times is it going there? It's going there 1,183 times. So I want the remainder. Subtract. That is 1,183 times. The remainder is 14,858. 14,858. Now square this line to get the next line. You can see I squared that. Square that. Now square this 14,858 times 14,858. You get now a huge number, 220 million. 220 million. Divided by our divisor, which is 17,449. It's going there, how many times? 12,651 times. 12,651 times. Let's find the remainder. 12,651 times. The remainder is 12,865. 12,865. Remember, we had decided we're going to go 15 times, or are they 15 times? So we are still proceeding. There are how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 times. We're going to go 15 times. How many have we gone so far? 1, 2, 3, 4. Let's go the 5th time. Square that. Let's square this number. Times 12, 865, 865. I'm getting 165 million and 508,225 divided by our divisor, which is 17,449. It goes how many times? 9,485. What is the remainder? Let me see. 9,485. The remainder is 4460. Again, square that line to get the next line. So I'm squaring 4460. I'm squaring 4460. I'm getting 19,891,600 divided by 17,447. No, 449. Divided by 17,449. It goes there 1,139 times. Let's find the remainder. I'm writing them there so that when you listen to the video later, you can compare what you'll be getting at that time. I'm getting 17,189 times. Now square that line to get the next line. I'm squaring that to get 295,461,721. Divide this by our divisor there, which is 17,449. And then it goes 16. This time it has gone there 16,000. 932 times. Did I divide correctly? Yes. Yes. Was there those number of times? Let's find the remainder. So it went there 16,932 times. And the remainder is 15,253. 15,253. Square that line to get the next line. Square that line to get the next line. I'm getting 232,654,009 divided by 17,449, which is our divisor. And we find that it goes at 13,333 times. The remainder, that was 13,333 times. The remainder is 6492. 6492. 6,402. Square that line to get the next line. Get the next line. 42,146,064. Divide that by our divisor, which is 17,449. It goes there for 2,415 times. What is the remainder? The remainder, after going there 2,415 times, the remainder is 6729. Square that to get the next line. Let's square that. You get 45,279,441. And our divisor is still the same, 17,449. Goes there 2594 times. What is the remainder? 2594 times. The remainder is 16,735, which we square to get the next line. After squaring, I'm getting 280,060,225. Divided by the same divisor, 17,449. And I'm getting that they will go there how many times? 16,050. So, but I'm interested with the remainder here. It has gone there 16,050 times and 50. The remainder is 3,775. Square to get the next line. So it's a very easy thing, just squaring a line to get the next, square to get the next. This is what we call the successive squaring method, or the fast powering algorithm. So when you square this, you get 14,250,625. Our divisor is the same, which is 17,449. Goes there 816 times. 816 times. 816 times. What is the remainder? The remainder is 12,241. We were to go 15 times. We are about there. So how many times have we gone so far? So you can see the advantage of converting this number to binary. You convert the power to binary. It will tell you the number of times you're going to go, that you are not scared, just going as you count. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We've gone 11, 12 times. We're left with 3 times to go. Let's square that number. Let's square that to get the next line. Square that. You get 149,000. 149 million. 149 million. 842,081. Divided by the same quotient. It has gone too far now. It was 12. It was 17,449. 17,449. It goes down how many times? 8,587 times. So what is the remainder after going there those number of times? 8,587 times. The remainder is 7,518. Square that to get the next one. Square that. I'm getting 56,520,324 divided by our divisor, which is 17,449. Goes that many times? 3,239 times. What is the remainder? After going there 3,239 times, the remainder is 3,013. Finally, we got the last lap. Square that to get the next one. When you square this, when you square that, what you get? 9,078,169. Okay, our divisor is what? 17,449. Going there 520 times, what is the remainder? The remainder is 46,89. So we've done everything. So the other advantage of that conversion from decimal to binary is that it will tell us which ones we're going to combine. It will tell us which one is we're going to combine. Let me just see here. The ones which have ones, beginning from this side. Just a minute. Okay, so beginning from this side, you can hear me, is that okay? Can you hear me? Okay. Now, what does this number tell us? The one which we're going to combine only those which have ones. Those which have ones. Let me see. 1, 2, 3. Going to combine the fourth one. Then we skip 1. Combine the sixth one. Then we skip 1, 2, 3, 4. Then combine this. Then skip and combine that. Okay, let's just go. Just a minute. Let me just again explain. Beginning from this side, beginning from the right-hand side, if you begin from the right-hand side, this is power 1, the first power. So it's this number here. So it means this number will not be part of our combination. So what it means that when you want to get the power, which is 17,447, you'll count 1, 2, 3, 4. The fourth one, just count the power 4. The fourth one. 1, 2, 3, 4. The fourth one going down, the fourth one going down. 1, 2, 3, 4. That is power 8. Then count again. This was the fourth one. Fifth. Then you take the sixth, the one which has a 1, sixth. this fourth, fifth, sixth, power 32. And then skip how many? 1, 2, 3, 4. Skip 4 and then take the next one. Skip 4. Let's just skip 4. 1, 2, 3, 4. Skip 4. 1, 2, 3, 4. Then take the next one, which is 10, 24. 10, 24. Let me just write it there. Plus 10, 24. 10, 24. We skipped 1, 2, 3, 4. Then took this. Then take the last one. Take the last one. What is the last one? What power is that? The power is this. 16, 384. 16, 384. 16, 384. Let's just see whether that is true. Let's just see whether that is true. Let's add them and see whether they add up to that. We've taken 8, then taken that 2, then take, just a minute, I'm multiplying, supposed to add 8 plus that 2, then plus 10, 24, then plus 16, 384, gives me, what is that? 16, it's giving me more by 1. What do I want? Have I added the correct things? Let's just go back and see. Let's go back to this number. 1, 2, 3, 4, the fourth one. We took 8. Took 8, and then skipped 1. Took that 2. Then we skipped 1, 2, 3, 4. Took the fifth one. After that 2, skipped 4. After that 2, skipped what? 1, 2, 3, 4. Took 10, 24, and then took the last one. How come the excess by 1? Is my number properly converted? It's okay. We'll check that. Let me just, are you also doing the addition? So that I could be adding and getting different things. Let me see what somebody has said here, if there's any assistance. Okay. That is 8 plus that 2 plus 10, 24 plus 16, 384. It's giving me more by 1. It's giving me more by 1. I think I'll avoid it this time. Then just go by what I did here. I took the last one, then took 10, 24, then I took that 2. So the difference comes in here. I have 8. I took 4, then took 2, then took 1. How many? 1, 2, 3, 4, 5, 6. How many ones do we have? How many ones do you have? 1, 2, 3, 4. These are only 4. I don't know why it's not working for this one. Because we're supposed to have, if we have, maybe my conversion. Oh, I've seen my conversion was not correct. My conversion, I was supposed to convert the power. I was supposed to convert the power. The power is, what's the power? What confused me was this. When I gave the answer here. The power is supposed to be 78, 14, no, 78, 14 raised to, the power is supposed to be 17, 4, 4. Huh? The power is correct. 7. Just convert this number to binary first. Or you convert to binary later. Just convert this number to binary. It's our power. Our power is this. Convert to binary and see whether it gives us, whether this is correct. Just confirm if this is correct. Because I'm seeing it could be where the problem is. That number could not be the correct conversion to binary. Correct conversion to binary. It's okay. I think that number is not correctly converted. So after that, then you have this. Just after showing that the number is not well converted, we have that. Then you just write. Now what I wanted to show you now is this part. This part is the one I'm referring to. That a calculator cannot do the whole of it. Calculator cannot do that. So you have to combine. To combine these two, then the answer you get combined with this, the answer you get combined with this, as you do mod 17449, the answer you get combined with that, and then in bits. But combining the three, even if you combine the three, the calculator will not do it. It will be huge than the calculator can accommodate. So just to deal with the two at a time. And then you'll arrive at this answer there. So the only assignment I give you therefore in suspecting is not well converted. Thank you.
Thank you, Daktari. I think more practice is required on our side. So see you on Thursday, where we can do more practice and keep moving forward. So thank you very much, everyone. Else, see you tomorrow with Wanjiro at 8 p.m. Asante.